Hello everyone, I'm Saivak and with me is Tanishka Keluskar.
Hi, we are from KG Sumaya School of Engineering and our project is fraud detection in online transactions. It is implemented using HashMap, sliding window queue, and priority queue.
The goal of our project is to design a real-time fraud detection system that identifies unusual activity in online payments and immediately flags them for review.
The problem we are addressing is the need to detect fraud transactions in real time. Traditional systems often identify fraud after the transaction is completed. Ours does it while it is happening.
We use data structures to store user history, analyze recent behavior, and prioritize high-risk transactions. This ensures that suspicious activity is handled faster than in conventional models.
For implementation, we selected three core data structures.
First is the hash map, which stores every user's transaction history with time complexity of 1 lookup time, perfect for instant retrieval.
Next, the sliding window queue, which only stores the most recent transactions, like the last 5 minutes, automatically removing older data.
And finally, the priority queue, which ranks suspicious users by their risk score, ensuring that high risk cases are reviewed first.
Together, these three structures form a vast, efficient, and real time data detection system.
Our system is implemented in Java using a rule-based approach. Each user ID acts as a key in the hash map and points to the queue of recent transactions.
This is the transaction class. It stores data like user ID, amount, time, and location for every transaction.
The fraud detector class handles transaction validation and the sliding window queue. Whenever a new transaction arrives, old entries beyond the 5-minute limit are removed automatically.
Next, the calculate risk score method. It assigns points based on amount, frequency, and location changes. If a user transacts rapidly from a different IP, their risk score increases.
Once a suspicious activity is confirmed, the user is inserted into a priority queue, which ranks users based on their risk score. The higher the score, the earlier they are reviewed.
In the main program, we initialize the hash map, process multiple user transactions, and simulate realistic patterns like high frequency payments and location jumps.
The console output displays messages like "Transaction safe" for normal users and "Suspicious activity detected, risk score 9" for risky cases.
This flow diagram shows how the process connects. Transactions are stored in the hash map, filtered by the sliding window queue, and finally ranked by the priority queue for alerts.
We validated our system using 7 test cases to simulate various fraud scenarios.
Case 1, normal low value transaction, which gives no alerts. Case 2, 3 high value payments in 2 minutes, high alert triggered. Case 3, new user, no alert because there is no history. Case 4, location change from India to US, which is IP alert.
Case 5, queue overflow. Older transactions are dropped correctly. Case 6, location jump. Hash map is updated and is also alerted. And last case, case 7, priority queue. Transaction 1 has a score of 9 and it is processed before transaction 2, which has a score of 6.
All test cases passed, confirming our data structure and logic worked efficiently.
The system achieved high accuracy, detecting high risk activity while ignoring safe ones.
The sliding window queue improved efficiency and reduced memory usage, while the priority queue ensured urgent alerts which were reviewed first.
This demonstrates the real-world power of combining algorithmic logic with practical data structures.
Our project shows that simple data structures can power complex real time fraud detection.
It's efficient, scalable, and accurate, proving that even basic structures like hash maps and queues can have major real-world impact.
Thank you for listening. Alright, that wraps up our discussion on the real time fraud detection system. Now we are excited to take up some questions from our peers.
We have Vedant and Sanmeet with us today, and they'll be asking about how our system actually works under the hood. Let's get started.
Hello. So my question is, your system uses a hash map for storing user history. Why is that the best choice for a system real-time setup?
Great question. The hash map gives us time complexity of 1 lookup time, meaning it can fetch any user's data almost instantly. In a fraud detection system, we need that speed to immediately check a user's past activity whenever a new transaction happens.
Exactly. That's what makes it perfect for our location jump check. If someone suddenly transacts from another country or city, the hash map helps us spot that change within milliseconds.
And since every user has their own entry, the system stays fast even with thousands of users at once.
You also used a sliding window queue. How does that help detect fraud and what makes it efficient at removing old data?
The sliding window queue helps us catch velocity fraud. When someone makes too many transactions too quickly, it only helps the most recent transactions. For example, those from the last few seconds. Any older transactions are automatically removed once they fall outside that window.
That's right. This not only saves memory, but also ensures we are analyzing the current activity, not outdated data.
And since every user's transactions are stored in their own queue, linked to the hash map, we analyze their spending speed separately. That gives them the system personalized accuracy.
Also, you have used priority queue for alerts. How does it make sure the most urgent cases are handled first, and how is the priority decided?
The priority queue works like a triage system. Just like hospitals handle critical patients first, each alert has a risk score based on amount, frequency, and location changes. The higher the score, the higher its priority.
So, if one alert has a score of 9 and another has 6, the 9 gets handled first. It's the simplest, most effective way to make sure we don't miss severe cases.
Exactly. It keeps our system proactive, not reactive, stopping fraud before it causes real damage.
Thank you, Vedant and Sanmeet, for those thoughtful and relevant questions. They really brought out the heart of our system.
We hope this gave everyone a clear view of how HashMap, sliding window queue, and priority queue work together to make fraud detection both fast and reliable.
That was a great discussion. Thanks everyone for joining.
Now, I would like to invite Sanmeet and Vedant to present their topic on priority queues in lived systems.
Hello, I'm Sanmeet Wale,
Hello, I am Vedant Pathri.
and today we'll be presenting on priority queues in lift systems, specifically on how we can use efficient elevator scheduling with data structures. Let's start with the fundamentals. What exactly is a priority queue? A priority queue is a specialized data structure where each element has an associated priority value that determines the order of service. This is fundamentally different from the standard queues that follow first in, first out principles. Unlike regular FIFO queues, priority queues serve elements based on importance, not arrival order. The most common implementation uses binary heaps, which are the industry standard because they offer optimal performance for insertion and deletion. Now let's examine the core operation that make priority queue so powerful. There are three fundamental operations: insert, which adds an element in assigned priority value; extract, maximum or minimum, which removes the highest or the lowest priority element; and peek, which allows you to view the topmost priority element in the queue. When we implement using binary heaps, we achieve excellent efficiency. Both insertion and removal operation runs in time complexity log n, and while peak operations, we use time complexity of 1. Now let's understand why elevators need such sophisticated scheduling. Modern elevator systems face three major challenges. First is scale, where we are dealing with hundreds of simultaneous requests across multiple floors and elevators, cars. Second, we have variable priorities. Emergency overrides, direction preferences, and cumulative wait time create complex scheduling. Third, there are dual objectives. We need to minimize passenger wait time while simultaneously reducing energy consumption as well. These these competing demands make elevator scheduling a perfect application for priority queue algorithms. So now I will have Vedant to explain the further.
So now the first factor here is the distance factor, which gives higher priority to floors closer to the elevator's current position. And the next is direction alignment. Elevators prefer requests that match their current movement, whether up or down. Then we have a wait time waiting, where passengers waiting longer slowly move up in priority. And finally, emergency override. Any urgent request like a fire or a medical emergency jump straight to the top. Now let's take a real-time example. The elevator here is on fourth floor. Now here we can see the floors requests are from fifth floor, eighth and second. And here there is an emergency request from floor 2. It gets the highest priority and is served first. Then comes floor 5 because it is in the same upward direction, and finally floor 8, which has the lowest priority. This way unnecessary stops are reduced and passengers are served faster. Using this system, modern Lift can handle many requests at once without bottlenecks. They are dynamically adaptable, meaning they can instantly change priorities if there are any emergencies. This reduces average waiting time by about 30 to 40% and also improves energy efficiency by minimizing extra moments. Overall, the system becomes faster, smarter, and more reliable. The code first collects all flow requests and splits them into up and down queues. Each queue is sorted so the elevator moves efficiently in one direction. Once it finishes one direction, it reverses to handle the other queue. This mimics real elevators, reducing stops and saving energy, all thanks to priority queues. This is our Turnitin report. To summarize it, we are a foundation where priority queues are essential for scheduling systems requiring intelligent request management, and in implementation, binary heaps provide complex time complexity log n performance, enabling real-time responsiveness in elevators. Application: multi-factor priority scoring optimizes lift dispatch, and in impact, smart scheduling improves user satisfaction, reducing energy waste, and demonstrates data structure power in real systems.
Thank you, Vedant. Now we'll have Sai and Tanishka to ask us questions about our presentation.
I would like to start with the questions. My first question is, why did you choose an elevator as your date scenario for the data structure?
We choose an elevator because it is a simple and relatable real-world system that everyone understands. Elevators deal with multiple flow requests and must decide which one to serve first. This is just like a priority queue where elements are arranged on importance, in our case, the nearest or most logical flow request. So it's an easy and practical way to explain how data structures can solve everyday problems.
Oh.
So next question.
How how does the elevator know which floor to go to next?
That's a good question. The elevator system gives each floor request a priority value. If it's moving upward, it gives higher priority value to the floors above, to the floors which are closer to it. And if it's moving downward, it prioritizes the lower floors which are nearby, and this ensures smooth movement in one direction until all requests that are served, reducing time and unnecessary direction changes.
Interesting. So, what happens if a new flow request comes while the elevator is moving?
When a new request comes, it is simply added to the priority queue. The elevator checks whether that request is in the same direction or not, and if it's already moving. If yes, it adds that stop into the current route. If not, the request stays in the queue and will be served once the elevator changes its direction. This makes the system dynamic and responsible to the real time inputs.
Oh. What data structures do we use to make a priority queue?
We typically use a heap, either a min heap or a max heap. For going up, we use a minimum heap because we want the smallest higher floor first. For going down, we use a maximum heap to get the nearest lower floor first. Heaps are used because they allow fast insertion and quick access to the highest or lowest priority element.
Alright, my last question to you is, what are the main advantages of using a priority queue in elevators?
There are many advantages to use a priority queue in elevators, such like it reduces the total travel time and it decreases the waiting time for passengers who are calling the lift. It avoids unnecessary up and down movements and thus it makes the system more organized and efficient. Overall, it helps the elevator work smarter by solving the most important requests first and improving the user experience also. Thank you for your questions. This is Sanmeet and Vedan from Group 7 signing off.
And Sai and Tanishka from Group 15 signing off.
Thank
Thank
you.
you.
Thank you.